Welcome back to part 2 of our IP version 6 routing lesson. Again, my name is Joe Reinhardt and I'm your instructor. This is part of the Cisco CCNP course training from TrainSignal. Now we're going to drill a little bit deeper into IP version 6 in the sections that we haven't already covered. In this lesson, we will continue our discussion of understanding and configuring IP version 6 routing. We will look at some of the many IP version 6 IP version 4 coexistence mechanisms, and then we will finally apply a number of these things that we've learned in our lab environment. We're actually going to examine under routing, we're going to look at BGP for IP version 6 and then a little bit about route redistribution. Let's consider BGP for IP version 6. The mechanics of the protocol, as with the others, it's very similar to its counterpart for IP version 4. It uses TCP port 179 for transport. There's still manually configured neighbor relationships. You still have eBGP, IBGP neighbor types. You're still using the same path attributes. You're still using the neighbor network statements. That's all identical. The difference is that unlike the other protocols, IP version 4 and IP version 6 are supported simultaneously on the same device. It's actually through a construct called the address family command. There's an address family IP version 4 and there's an IP version 6 construct as well. There's also a multicast mode that's supported with BGP for IP version 6. To configure IP version 6 BGP, you again first have to enable IP version 6 routing using the IPv6 unicast routing command from global configuration mode. And then the process itself is created under the command address family IPv6 under the currently existing BGP routing process. This refers back to what I mentioned a moment ago. There's an address family for IP version 4 and an address family configuration section for IP version 6. Neighbors are still manually configured. It's the neighbor IP version 6 remote ASN autonomous system command. None of that's any different. One of the things that is particularly important is that after you configure your neighbor and put in next hop self or whatever else you need to, you have to do neighbor IP version 6 address and activate. You have to activate the neighbor in this particular address family. That will be the final step you need in order to bring the neighbor relationship up, providing there's no issues with connectivity. Networks are injected into the process the same way they are in IP version 4. You use the network prefix, mask, and so forth, or you use the redistribute commands. The show commands are also very simple. Show IPv6 protocols, show IPv6 route BGP, show IPv6 BGP, and as we demonstrated in our last lesson, you can actually show the individual neighbors and so forth. To redistribute routes in IP version 6, again, it's very similar to the mechanics in IP version 4. Don't let the different formats and addressing throw you off. There's a great deal of similarity. It's still routes are redistributed from the IP routing table. It uses the same administrative differences. Route filtering and manipulation is similar. Distribute lists, route lists, prefix lists, all that is the same. And the command syntax is almost the same as well. A couple differences, just to highlight these. OSPF version 3 does not require the subnets keyword to import all the routes. Again, this is because there is no concept of classful routing in IP version 6. It's all classless routing, so there's no need to include it. So again, the cause of grief that happens with the subnets subcommand, you don't need to worry about. Connected routes are not imported from a particular protocol without the include connected command. In other words, if you do redistribute EIGRP 100, for example, the IP version 6 process is not going to import any of the routes of the connected routes participating in EIGRP into the process without using the included connected command. Access lists and prefix lists obviously use IP version 6 formats rather than IP version 4 formats. That's another difference as well. Configuring redistribution, very straightforward. Again, IP version 6 unicast routing, always start there. Then underneath whatever protocol you're redistributing into, it's connected routes, it's redistribute connected. You don't need to put anything else if you don't want to, but then you can obviously specify the metric or route maps or so forth. For BGP and RIP next generation, the syntax is pretty similar. Redistribute RIP process, or redistribute BGP ASN, and then again you can specify the metric and route maps and other things if you want to do additional filtering. For EIGRP, redistribute EIGRP autonomous system number, and you can include the include connected in order to be able to take care of the problem we talked about a moment ago. With OSPF, almost identical, except you can match the route type, internal, external, and so forth. The show commands for verification are very similar to those used for IP version 4 redistribution, just with the IP version 6 keyword. IP version 4 has been around a long time, has a lot of strengths, obviously has some issues as well. IP version 6 is essentially what's called the new kid on the block, but it's not going to be taking over wholesale anytime soon. Obviously, in parts of the world where there is no IP version address space at all, for instance, Asia Pacific, it's already in operation. But frequently in the real world, as well as the CCNP route exam, you need to understand transition mechanisms, ways that these protocols can coexist and in some cases share information. So there are essentially three basic approaches. There's dual stack solutions. In other words, having both an IP version 4 and IP version 6 stack active. There are various tunneling mechanisms, and there's an incredibly large amount of them. And then there's what's called NAT-PT, or NAT Protocol Translator. And usually the preference, if easing into an IPv6 implementation, is you start with NAT-PT if you need to, then do dual stack, and then do tunneling mechanisms. Typically IPv6 IP, but we'll talk about that in the contents of the lesson. Again, first there's dual stack solutions. This essentially deploys both IP version 4 and IP version 6 side by side, and it's sometimes called ships in the night routing because they're working alongside, but they're not sharing information or integrating in any real way. The applications ultimately choose which protocol to use. This obviously requires IPv4 and IPv6 addresses and routing to be configured on all the devices. This can be the case with laptops, workstations, servers, routers, switches, and so forth. Typically, a dual stack is going to be the best solution for coexistence because it's a lot simpler and most of the devices that are out on the market already support both. For instance, Microsoft Windows hosts, Windows Vista, Windows 7, not only have IP version 6 as part of their protocol stack, but actually prefers IP version 6. Now, obviously, one of the drawbacks is you need to have double configuration on all the devices. For instance, in the graphic to the left, you can see in our lab, we have router 1. We have an IP version 4 address, 172.16.134.1/29, and then an IP version 6 address on the same interface, 2001 C926.101.134.1/112, and something similar for router 3. Twice the configuration, twice to manage, twice to deal with, but usually the easiest way to ease into IP version 6. Aside from dual stack solutions, which are remarkably straightforward, there are a variety of tunneling mechanisms. First, there are manually configured tunnels, sometimes just called MCT. Obviously, this requires the use of tunnel interfaces on both ends of the connection. Just for a reference point, we have our lab here. We have router 9 and router 5, and you can see there's a tunnel built between them. Well, a manually configured tunnel has to have a valid IP version source and destination using the tunnel source and tunnel destination commands. You can use tunnel source, for example, a specific interface or an IP address. Obviously, for tunnel destination, you want to have the destination IP version 4 address. Tunnel mode for a manually configured tunnel must be specified as IPv6 over IP, which the keyword is tunnel mode IPv6 IP, not tunnel mode GRE. That's something altogether different. Then you want to be able to verify successful configuration. The tunnel interfaces should show up. If it's not reachable, it'll show up-down perhaps, and you should be able to ping and reach the other side of the manually configured tunnel. You also have to put on your IP version 6 parameters. You obviously have to have IPv6 addresses on both ends of the link. You have to then put your routing commands on, either static routes or dynamic routing protocols. And then you verify that it's operational with show IPv6 route connected or the IPv6 ping or trace route. Another type of tunnel are not manually configured tunnels, but automatic tunnels, ones that automatically do some type of configuration. These have very unique characteristics. For instance, 6-to-4 tunnels, which we'll talk about first, very unique characteristics. It's essentially used to join multiple isolated IP version 6 domains together. You can kind of think of it as the Hawaiian Islands. Each has its own IP version 6 infrastructure, but they don't have any way of communicating with one another, and that's where 6-to-4 tunnels come from. Unlike the manually configured tunnels, it is a multi-point type of tunnel, not a point-to-point tunnel, meaning it can actually have multiple endpoints. And IP version 4 addresses are embedded in the IP version 6 addresses in hexadecimal. There's an option for doing it with global unicast addresses, and then there's also an option for using the 2002:/16 reserved range. This is frequently used for 6-to-4 tunnels if there isn't going to be any traffic going to the global internet. Configuration of the IP version 4 compatible tunnels. First, the tunnel mode has to be specified as IPv6 over IP, but auto mode, tunnel mode, IPv6 IP, auto tunnel. And this is the compatible address format for the encapsulation. The tunnel source is typically tied to a local IP version 4 loopback address. And then the IPv6 address is created using obviously the leading zeros, and then the IP version 4 address embedded, pointing to the other side. The final part of this is you actually need to use BGP in order to be able to facilitate communication across the link. So obviously you need to go into the address family commands as we talked about, and we'll actually be doing this in our lab. And then you can verify whether or not it's operational by show IPv6 route connected, show IP BGP, show IP route BGP, show other commands as well, and then obviously the IPv6 ping or trace route commands. Another tunnel requires more configuration, but it's called an ISOTAP tunnel. It stands for Intra-Site Automatic Tunnel Protocol. It's used to join multiple IPv6 domains together. Again, it's multi-point in nature, and it uses IPv6 global unicast IP addresses. Some of the unique characteristics is the IP version 4 address are embedded in the last 2 octets in hexadecimal using the IPv6 prefix, whatever it is, and then the AABBCCDD at the very end. Tunnels usually use a single prefix, a common IPv6 subnet, and you can also optionally use modified EU164 rules. Configuring it, obviously tunnel mode, IPv6 IP ISOTAP, tunnel source, loopback, whatever the local loopback is, and then creating the IPv6 address using the format that we talked about. Again, you can use Excel to make this easier for you. Once you're done, you have to create static routes in order to be able to share information. So you'll do the IPv6 route, prefix length, tunnel, and then the interface, and then show IPv6 route, and then ping and trace route. We'll show whether or not the ISOTAP tunnel is working. You'll see that in a number of these mechanisms, there's a lot of static routing involved. There are, however, some additional tunneling methods that are available. One is GRE tunneling, which is very familiar to most people. It's been used in a number of different instances and settings. It's virtually identical to manually configured tunnel. The only difference is the tunnel mode would be specified as tunnel mode GRE IP. We'll be configuring that, in fact, to the graphic to the left in our IPv6 EIGRP between router 5 and router 9, we'll be doing a GRE tunnel. And one of the things GRE allows is for dynamic routing to be used across the tunnel, unlike the manually configured tunnel and some of the others where the routing has to be static. Another type of tunneling is called Teredo tunneling. This is essentially developed by Microsoft. It bypasses NAT. It's not used just for Microsoft, but you will see, for instance, when you do an IP config command on a laptop running Windows Vista or Windows 7, you'll actually see a Teredo interface as part of the stack. Another coexistent mechanism is sometimes referred to as NATPT. It stands for NAT Protocol Translator. It's very similar in operation to the NAT with IP version 4. The difference is obviously it's not going from private addresses to globally routable addresses, but it's actually between IP version 4 address and IP version 6 addresses. So you still have static NAT, dynamic NAT, and overload or port address translation. You can see the graphic to the left. The idea is you're taking the IP version 6 address to the upper right and translating it to the routable address on the other side and using a NAT boundary. Now, some of the differences in the protocol is there's an option called IPv4 MapNat, which it's using a predefined IPv6 prefix as part of the equation. Bridged virtual interfaces are not supported with NatPT. And then there's some limited application layer gateway support. So ALG, as it's sometimes referred to, DNS, ICMP, and other things are going to have limited support with NatPT. Configuring it, you obviously have to identify the IPv6 addresses to translate using the IPv6 NAT prefix and length command. You specify the addresses, and then you specify the interfaces using the IPv6 NAT subcommand on the interfaces. If you're going to use mapped NAT, you add the v4 mapped keyword after the prefix statement. If you're going to do static NAT, you just define the translation just as it is with IP version 4. You do IPv6 NAT, version 4 to version 6, and version 6 to version 4 source commands. For port address translation, you use this particular set of steps. Just as in IP version 4, you define the addresses to be translated using an access list, the IPv6 access list command. You create the mapping on an interface. You could do this with a pool as well, but you can use an interface command IP version 6 NAT v6 v4 source list, the access list, interface, type and number, and then overload. Verification, show IPv6 NAT statistics, translations. You can clear it with clear IPv6 NAT translation star, and then obviously you can do a debug on it as well. Now, quite honestly, NatPT is considered somewhat obsolete, and it's not usually a recommended transition step. For those wanting to get into it, it can be an easy way to try it out, but it's not generally considered a best first step. Dual stack is going to be the most preferred, and then tunneling mechanisms last, usually right after that, using some type of tunneling mechanism, and one of the common ones is 6-to-4 tunnels. Now we're actually going to take what we've been learning throughout the various lessons so far and actually applying them in a lab environment and essentially a realistic environment using IP version 6. We're going to start by reviewing the configuration commands that we'll need to use, the devices that will be affected, configuration of the actual devices, and then obviously verifying that it's operating as expected. So first, to the left, you'll see a graphic of the IP version 6 domain. Obviously, the devices that are unaffected are largely left out, but we want to be able to use this as sort of a reference point. But we'll obviously have to start with assigning our IP version 6 addresses. We'll start with, obviously, the IPv6 address prefix length. These are going to be defined on loopback 6, namely a reference for IP version 6, on all the affected devices. So this will be the router 1, router 6, router 3, router 5, router 4, router 7, and router 9. So aside from the loopback interfaces, there are certain WAN and VLAN interfaces we will want to actually use. On router 1, the multi-point interface serial 00.134. Router 3 and router 4's serial 0 interface, because we configured everything on the natural interface. Router 1 and router 3 FA0/0.13, the VLAN interface. Then we'll actually be configuring a number of tunnel interfaces, one between R5 and R9, which will be a GRE tunnel. Then between router 1 and router 6, we'll be doing IPv4 compatible tunnel configuration. And then between 6 and 7, we will have a manually configured tunnel as well. Obviously, to start the routing, we'll be using the IPv6 unicast routing command from global configuration mode. We will then configure the RIP next generation process on routers 1, 3, and 4, the IPv6 router RIP process name, and then placing the protocol on the interfaces using the IPv6 RIP process name enable command. Then, because we'll be using a GRE tunnel between R5 and R9, we'll be able to use that as part of our EIGRP process. So we'll start the IPv6 router EIGRP ASN command. We'll enable the process underneath the interfaces IPv6 router EIGRP autonomous system number, starting the process, and not doing any type of route filtering, which is basically going to be standard throughout most of this. And we'll configure our tunnels specifically. Our GRE tunnels will be obviously tunnel mode GRE IP, source, which we'll be using the IPv4 loopback, The destination will be the loopback on the other side, and then obviously the IP version 6 prefix and length. The manually configured tunnel mode IPv6 IP, the source destination, similar to the GRE tunnel, but it won't be carrying any routing information, and then the address, and obviously the static route that we talked about, IPv6 route prefix length next hop. The final tunnel we'll be configuring will be between router 1 and router 6 using an IPv4 compatible tunnel. Tunnel mode IPv/IP auto tunnel. Source will be the loopback interface. Then we'll be using the IPv6 address with the 6 zeros and then the IPv4 address after that. And then we'll be using the address family IPv6 subcommand under BGP. The devices that will be involved, we've already talked about this. Router 1 on VLAN 99. Essentially, it'll actually be across the tunnel, but it'll be still involving that. The serial 00134 interface, loopback 6, and obviously the tunnel interface that we're talking about. For router 3, it'll be the VLAN interface, the frame relay serial interface, and obviously the loopback. On router 4, it'll only be the serial 00 and loopback interfaces. On router 5 and router 9, the EIGRP domain, just loopback and just tunnel interfaces alone. Having the loopback actually makes it easier to see visibility because the tunnel interface will be considered a connected route, not an EIGRP route in the routing table. Router 6, we have the VLAN interface, kind of, the loopback 6 interface, and the tunnel interfaces. And for router 7, the manually configured tunnel, obviously we will have loopback 6 and the tunnel. So as we go into the lab, we're actually going to configure using the following prefix. It's going to be 2001 C926 101, and then in the case of the loopbacks, the router number is represented by the numbers N here, and then it'll be a /128, meaning it's essentially a single host address. The frame relay interfaces, same prefix, but it'll have be 134, meaning between routers 1, 3, and 4, and then obviously the router number. In addition to that, we're going to have to map IP version 6 protocols across frame relay, much as we did with the frame relay map IP statements. Then we'll configure our GRE and manually configured tunnels using the same prefix, but obviously we'll be using both the router and the neighbor router numbers as we configure these. Like for instance, between router 6 and router 7, it would be 67 and so forth. And then obviously the IPv4 compatible tunnels, we've already talked about the addressing format. Static routes for the manually configured tunnel sites will be necessary. RIP next generation, using the process name IPv6 RIP, EIGRP on R5 and R6, using the autonomous system number 100. Now we're actually going to perform our IPv6 lab exercises. We have router 1, we have our console that we've talked about. We actually also have our entire configurations. So we're going to start with our loopback 6. Notice it's all ones. Configure terminal. Except that's not the statement we were looking for. Have to remember to actually use the command copy. So that's now working. We can put in our frame relay statements. And our basic interface command for its additional interface. So that takes care of the initial configuration on this router. Now we can get to router 3. Now we can actually configure our router 3. We have our configuration here that we need to paste. All successfully pasting it in there. Now we can configure router 4. Again, using Notepad can really save a tremendous amount of time. Okay, and it looks like we maybe missed one thing here. Here we go. That finishes writing the configuration. We can get down to what we need for router 5, which isn't very much. So all we're going to do in that is just putting in router 5 and router 6 and router 7, pretty much just these loopback interfaces, because we're going to be actually creating tunnel interfaces. So router 6. Now router 7. Always helps to be in configuration mode. I keep forgetting to put in the IPv6 unicast routing. So let's IPv6 unicast routing. Now we'll go to R9. IP version 6. Configure terminal. IPv6 unicast routing. And we can get the loopback interface we need. And that completes the basic configuration part of our lab. Now we're actually at the part of our lesson where we're going to configure the IP version 6 labs that we've been talking about. We'll start with just some basic configurations, interfaces, and so forth, and then we'll go on to the more complex aspects. As I explained before, one of the best ways to be able to take care of lab configurations is to perform them in Notepad first, and you have a reference point, and then you can easily paste in what needs to be done. You can see here all the basic configurations. Remember, we have the way we defined our loopback addresses. Loopback 6 is going to be the primary loopback address in the IP version 6 labs. We've got some frame relay configuration, and then obviously some other things here. So these are going to be the interface configuration, just the basic configurations you can see here, and we're going to go through the process of pasting them in. This is all for router 1. So we highlight it, we copy. Here's router 1 right here. Configure terminal. We paste in all of our configuration. You notice here some important things. You have the IP version 6 address command, IP version 6 enable. If you remember on frame relay, you have to actually map the layer 2 and layer 3 addresses. So we've got that there. Then we've got the fast Ethernet link between router 1 and router 3. So let's go back. Now we can take the configuration for router 3, also very similar. Copy. Go to router 3, configure terminal, and all the basic interface configuration commands. We'll do a write mem. Same thing with R1, write mem. Back to our configuration in Notepad. Router 4, of course, is going to be the last part in what we've been calling our EIGRP section of our lab. Here we go, configure terminal. Then we paste the configurations. It should all go in pretty easily. Do a write mem. R5. R5 is going to be one of the routers that we're going to be using some of our IP version 6, IP version 4 coexistence mechanisms. Configure terminal. That one's extremely simple. Now we'll go back to router 6. Router 6, if you remember, is one of the border routers we also used in our BGP lab. Configure terminal and paste. Write mem. Router 7. copy, configure terminal, paste, write mem. Then router 9 is going to be the last of our basic configurations. Again, just to loop back addresses, we'll be configuring more when we do some of the tunnel configuration that we've talked about. And write mem, and write mem. And we'll go back to our configurations. So one of the things we're going to do is actually configure and enable IP version 6 routing using RIP next generation. So we'll start with router 1. Write mem. We can actually go back here and notice here, first we have to do IP version 6 unicast routing. So we'll do that first, and then we'll paste the rest of this in. So configure terminal, because if you don't configure IP version 6 unicast routing, nothing else will work. Now we can see this is how we enable the RIP process in IP version 6. We're going to do no split horizon just because there are still split horizon issues. Now we actually want to put each one of the interfaces in the IP version 6 RIP process, which is what we're looking at here. So copy, go out of, remember this is configured under the interfaces. Always helps to actually copy correctly. Now if we were just to do show IP version 6 protocols, you'll see that it's actually correctly identified the interfaces, and of course there's nothing for it to peer with yet, but we'll start to take care of that with router 3. Copy. Go back to router 3, configure terminal. So we've enabled the process. Oh, notice we got the message here, IP version 6 routing not enabled. So we have to go back, IP version 6, unicast routing. Again, this is where the magic happens. All right, go back to our lab, configurations. There we go. Now we can do show IP version 6 protocols. You might even be able to say show IP version 6 route to see if any of the RIP routes are being propagated. And notice right here, this is the loopback 6 interface on router 1. Notice the same administrative distance, and we know it's 2 hops away, so all the rest of the mechanics are the same. So now let's go back and do router 4. Configure terminal, IP version 6, unicast routing. Now I can put all the configuration in. And I always seem to forget that because it's an older router, the syntax is just a little bit different. So we can do show IP version 6 protocols. Now we can do show, actually let's go back to router 1 and do show IP version 6 route RIP. Notice here we've got router 3, which we'd expect to see, and router 4. So this is actually functioning the way it's supposed to. Also look, notice you've got your link local addresses. So these are some things that are important for you to remember. So now that we've enabled IP version 6 RIP, now let's look at IP version 6 for EIGRP. What we're going to do on this particular configuration is we're going to use a GRE tunnel. I happen to have a very soft spot for GRE tunnels because they not only allow you to take non-IP version 4 native protocols over an IP version 4 network, but it'll also enable routing protocols to operate and some things like that. So what we're going to do here, you see this is just going to be a basic tunnel, interface tunnel 0. Got your IP version 6 address. All the other, some things that I'll point out here, the tunnel source, we're going to use loopback 0 as our source, so the IP version 4 source will be 10.5.5.5, and then you specify the destination is 10.9.9.9. So the first thing we'll do is we'll go to router 5, configure terminal, and let's just configure the tunnel first before we start doing any of the other things. So we'll go ahead and paste it all in. Copy. Now this is important. Whenever you first configure a tunnel, it'll say line protocol interface tunnel 0 has changed state to down, because unless the other end is reachable by IP version 4, which in this case we have by 10.9.9.9, it won't come up. So it's showing the tunnel is up, up. Now we'll go ahead and go back and we'll create the IP version 6 EIGRP process. Copy. Now we paste that in. We want to make sure that we put loopback 6 and also put that in the IP version 6 EIGRP process. So we were to do the show IP version 6 EIGRP interfaces, tunnel 0, and it's not showing loopback 6 as being in the process, so let's just take a look and see what might be wrong there. Because it makes it easier putting the loopbacks in the processes. They're always one hop extra in the, considered an extra hop in the router. It's easier to identify that way. So now notice here it is enabled. So we'll do right mem. We'll come back to that in a minute. Now we'll go to router 9. We'll go ahead and do the same process we did before. Copy. Configure terminal. And here's the culprit. We don't have IP version 6 unicast routing enabled. So I'll repaste everything in. I wonder if that's the culprit here too. So we'll do IP version 6 unicast routing. So let's do show interface tunnel 0. Show IP interface brief. Let's do show run and just take a little bit of a look at the configuration. So we've got our loopback 6 that we talked about. Got it enabled on the tunnel source. Now since it's showing down, let's ping 10.5.5.5, and it's showing up. So let's make sure, oh look, the loopback 0 was missing. So this is another reason why it wouldn't work. So configure terminal, interface loopback 0. And remember the IP address for IP version 4 is 10. We're always using the router number, so it'll be 9.9.9, 255.255.255.255. Exit. Now notice the tunnel just came up. So now if we do a show CDP neighbors, well, we don't have it enabled on the tunnel, but if we wanted to, we could certainly do that. So now let's go back and get the IP version 6 EIGRP configuration. Now we'll do configure terminal, create the process. Now let's do show IP version 6. Notice it's already showing the adjacency. Using, remember, FE80 is a link local address, and it's configured, actually just operates that way. So now if we do show IP EIGRP neighbors, it actually just shows that, oh, that's because we're doing IP and not IP version 6. It's IP version 6 EIGRP neighbors. Ha! And there we go. Show IP version 6 route. We've got things working the way we wanted them to. So that's how we are configuring EIGRP. So we've got couple final things we're going to do. You remember the IPv6 transition mechanisms? We're actually going to configure a manually configured tunnel between R6 and R7. Remember, manually configured tunnel requires static routing, which is why we have a static route identified here. What we'll do here, first, let's go to router 6. So configure terminal, make sure we have IPv6 unicast routing. And let's just make sure we've got our loopback 6 and other things like that in here the way they're supposed to be. And here we go, our loopback 6 address right here. When it says no IP address, it just means no IPv4 address. So now we can go and notice here the terminology is very similar to what we've already had before. So we've got tunnel 1, we've got our IPv6 address that we've defined. The source is loopback 0, which remember IPv4 address, and then we're putting the destination address as the loopback on router 7. And remember, manual tunnel configuration is just IPv6 IP. So let's copy this configuration and paste it in. Notice that the tunnel came up right away, which isn't a surprise. So now we'll actually paste in the static route to the IPv6 loopback 6 address on the other side. Okay, do a write mem. Now we will go to router 7. Similar configuration, but it's just pointing the other direction. So we'll go ahead and copy all this. Copy. Now we'll do configure terminal. Make sure we have IPv6 unicast routing, which already should be there, but again, it's very important. Here we go. We've got all that in there. Shows tunnel is up. So now let's try to ping the IPv6 address on router 6. Ping. And there's a leading character that's causing it not to recognize it. So let's do ping IPv6. Oh, and it always so helps if you don't leave the prefix on the end for pinging. And there we go. So let's do we seem to have a bit of a problem here. So let's actually go back to router 6, make sure we've got everything correct. So here's our tunnel address. Well, this would explain a lot because it's saying loopback 6 is with all these 3s, and that's not correct. So let's correct that address. First, let's do show IPv6 route. And it is identifying that correctly. So that part of the configuration is wrong. So let's just double check what we have. Show run. So let's look at what we have to correct here. So that's correct, because that's on the other side. So really all we have to correct here is the loopback address. So configure terminal, and interface loopback 6. Now, what's incorrect in our configuration is these should be this address. So copy. Oh, always helps to put IPv6 address. IPv6 enable. Now let's go back to router 7 and try to do that ping again. And voila, now it works. This is a great example of how to do troubleshooting on IP version 6, as well as some just verification. So the final thing we're going to work on in our IP version 6 lab is actually the automatic tunnel configuration. Remember, this requires use of BGP, use of a IP version 4 to IP version 6 compatible address, and you can actually see how that's defined here. So we're actually going to go through and work on this. Remember, the reason why this works is because the IP version 4 address is embedded in the IP version 6 address, and that's kind of how it works. So now let's go back. We're going to go to router 1 and router 6. So we actually started out our exercises on router 1. So configure terminal. So we already have loopback 0 configured, but in this case we're actually going to put an IP version 6 address on loopback 0. So there we go. Now we're going to create the tunnel. Notice it does not say what the tunnel destination is. That's going to be supplied as part of the rest of this configuration. So and notice here the keyword auto tunnel under the tunnel mode. That's important because this is the automatic tunnel configuration. There we go. Notice it's not automatically coming up. It says, well, there we go. Now it's coming up. And so this is key because in BGP, we're actually going into the address family configuration. We're going to define the neighbor using, remember, it's these concatenated zeros. It's very similar to the rest of what we've talked about, but then the announcing the routes that we're talking about using here, which is right up here. So let's go ahead now that we've configured the tunnel. So let's get out of the interface configuration mode. Now, make sure we put this in. Now again, this is one of the things that's very important. You have to put the activate command. So we'll do a write mem. Now we can go to router 6, configure terminal. Again, we're doing the same thing. We're putting an additional address on loopback 0. Now we'll create the tunnel interface, again with the auto tunnel keyword. Recopy. Tunnel comes up. As we talked about, now we're going to create the BGP process from the router 6 side. All together there. Now we will wait for the BGP process to come up. We can start by show interface tunnel 0. Shows the tunnel is up. Now show IP version 6 BGP. Just do show IP BGP summary. You should see the IP version 6 neighbor configured there. Oh, notice here, it's actually showing that process is up. So show IP BGP. Notice here we can actually do a number of different things, but in this particular case we can do show IPv6 routes. Notice here BGP is being announced. So let's test connectivity. Ping. Remember, BGP. So let's go ahead and ping this address. And I have to remember to take that off of the end. And there we go. So this is all of the IP version 6 configuration labs. You can see we were able to successfully configure all of these different elements to be able to give you a sense of the different mechanisms you can use in working with IP version 6. So to verify configuration of IP version 6, which we actually did in our lab exercises a few moments ago, remember this is the graphic to the left is the basic representation of what we did. We wanted to make sure that IP version 6 itself was working correctly. You can use show IP version 6 interfaces, make sure that they're operational. You can do the show IPv6 route connected command, be able to make sure that what you've configured is actually working. Show IPv6 protocols, which we did a couple of times. It'll show you that the process is running and enable you to be able to not only verify the network and subnets, but also the interfaces that are involved, much like to the graphic to the left. Make sure that the presence of what networks you're expecting, which we did with the IPv6 route RIP command in RIP, and you can also do show IPv6 RIP and then the process name and actually show a lot of different details. When we confirmed IPv6 EIGRP, we were able to do show IPv6 protocols, again pictured to the left, verified that the process was running, the correct network, subnets, and interfaces were correct. You can also use show IPv6 route EIGRP to see the presence of the correct networks, and also do show IPv6 EIGRP interfaces, show IPv6 EIGRP neighbors, and so forth. Showing the interfaces, again, show IPv6 EIGRP, the autonomous system number in use. Interfaces, make sure the correct interfaces are there, make sure the correct autonomous system number is configured, because just like with IPv4, it's not going to work if the autonomous system number is not correct. Make sure that the peers that are listed in the interface summary actually show non-zero counts for neighbors on interfaces you expect neighbors to be on. Obviously, loopbacks you would not. And then you can look at the topology table with show IPv6 EIGRP 100 in the case of our lab topology. It'll show you successors, feasible successors, and all the other information that you're accustomed to seeing with EIGRP. Making certain that IPv6 static routing is working correctly, which if you remember, with the exception of GRE, all the other tunneling mechanisms require static routing of some type. The exception of that, of course, is with the auto tunnel. But you can show the IP interfaces tunnel with the tunnel number command. Make sure that the interface state is up. Remember, up is the physical, which with tunnels is kind of a misnomer. But the second up is the line protocol. And if you remember, when we actually had the correct endpoint identified, it would bring up the tunnel layer 2 protocol. Make sure the source is correctly identified, the interface is operational. Then you can look at the show IPv6 route static command, which we just did show IPv6 route on a couple of occasions, and it does the same thing. Make sure the right routes are present in the table, and the next hop is correctly identified. Another thing that you can do, which we actually did, if you remember, we found a mistake in the configuration, went back and fixed it. We were able to do that because the ping was unsuccessful. So you can use the ping IPv6 command to verify reachability. You can use traceroute to review the path. And then, as with everything else, you can actually use application layers like Telnet to be able to verify full application layer reachability, which is actually sort of the acid test of a fully operational network. So just in key terms, we want to review dual stack. If you recall, this is one IPv4 to IPv6 transition mechanism where you actually configure both protocols actively on all devices and all interfaces on those devices. MCT is the manually configured tunnel. This is one of the transition mechanisms that you create a point-to-point tunnel to bring IPv6 traffic across an IPv4 domain. We did this between router 6 and router 7. 6 to 4 is an automatically generated tunnel, which is another transition mechanisms, but it's a multi-point tunnel rather than a point-to-point tunnel. If you remember, GRE and MCT are both point-to-point in nature. And typically you use 6 to 4 to bridge together multiple isolated IPv6 domain. Then there's ISOTAP, intra-site automatic tunnel protocol, and this is another mechanism. It's also a multi-point tunnel, and it uses global addressing, whereas 6 to 4 addressing can use either a private range or a global range. When you use the global range, you have to do some extra configuration. And then finally, NAT-PT, NAT Protocol Translator. This is another transition mechanism in which IPv4's addresses and IPv6 addresses are translated using a form of network address translation. So what have we covered? A great deal. Understanding and configuring IPv6 routing, a continuation from the previous lesson, looking at EIGRP, for example, and BGP. IPv6 and IPv4 coexistence mechanisms, manually configured tunnels, dual stacks, NAT protocol translator, and so forth. And then finally, configuring and verifying all aspects of our IPv6 lab exercises. Thank you for your attention, and we'll be continuing with our lessons shortly.